Alright, so hello everyone. Okay, so I'm just waiting for you guys to join the class. Do let me know whether I'm audible or not. Okay, so that we can start. So today we'll be discussing about organometallic compounds, and we'll solve questions related to that, right? So I'll just wait for a few minutes so that others also can join the class, and then we'll start it. Namaste, Robin. Hello. Okay, 2 minutes, huh? We'll just wait. Okay, so I'll just start it. Let others join in the between. We'll just do the intro part till then. So organometallic compounds is one of the important and one of the most scoring part from your from your inorganic chemistry, apart from your coordination chemistry. Okay, and it can easily give you around like 12 to 16 marks or more, even more than that. Okay, so these classes are provided to you by Unacademy Plus program, and these are all free live sessions. Good afternoon, Neelam. Okay, so these are all free live sessions, where you get classes on YouTube. Although you can also join an Academy Plus for a very like detailed and a very like a very organized classes. Okay, so on Unacademy Plus we have a course, complete course, in which we have organized classes for dealing with different topics. In those classes you will get like detailed explanation of the topic. You'll also get problem discussions over there, so that whenever you have any problem you can discuss that out with the educator. You also get recorded class, so if you miss out any of the class you can watch the recording of that. Then we have a regular like we have doubt clearing sessions at regular interval. In case you have any doubt in the class, you can clear that out in the doubt clearing session. And we also have a WhatsApp group where you can discuss out your doubts and like clear out whatever you have over there. So if you are planning to take an Academy Plus subscription, you can do that by using my referral code. So while taking subscription, just use my referral code, that is N_Huda. If you use this referral code, you'll get 10% discount on the subscription fee, and also you'll get access to all the other benefits of the Unacademy Plus classes. Okay, so without wasting much time, we'll just start organometallic compound. So what I'm going to do is I am going to take questions. Okay, we'll be having questions and we will be discussing them over here in the class. Okay, so I just want your active participation in that, so that we can discuss that out and we can clear that those questions and other things. Okay, so that's the benefit of live class, so we are going to take advantage of it. Okay, so let's start with the first question over here. So this question was asked in like all the questions which I'm going to take will be taken from the previous years of your CSIR net exam. So over here it says that the tungsten bond order in this complex, the complex given to you is this, that is you have tungsten eta 5 Cp. Okay, it's C5H5, that means eta 5 Cp. You have mu Cl, okay, that means a bridging chloride is there. Then you have CO, that means carbonyl ligands are there, two ligands of that and hold twice. So you have to tell that how many tungsten bonds are there. This topic comes under metal bond, finding metal bonds. Okay, so how we do that? First of all, we calculate total valence electron. So let's try to do that. Total valence electron. So tungsten, what kind of species is this? Like tungsten comes under which group? It comes under chromium, right? So chromium, molybdenum, and then tungsten. So so chromium is like, if I just talk about chromium, so chromium is nothing but it has 4s1 and 3d5 configuration. Okay, so this is the configuration of your chromium. So it has 6 electrons over it. So once I calculate, so same thing will be with the tungsten also. Okay, we'll be having similar thing with tungsten. So if I just write down tungsten over here, it will not make any difference. Okay, so tungsten will have this configuration. Fine, that means we have 6 electrons in it. Let's try to find out total valence electrons. So that will be calculated by this 6 electrons from this tungsten. Then eta 5 means it is donating 5 electrons. So this cyclopentadienyl ligand will give you 5 electrons. Whenever you have halogen in the bridging form, bridging halogen, this always gives you 3 electrons. Okay, so remember that. So 3 electrons from here, and then you will be getting 2 electrons from each carbonyl ligand. So 2 into 2, that will be like 4 electrons from here, and whole twice, so we'll just multiply this whole value with 2. So what I'm going to get is 6 plus 5 11, 11 plus 3 is what, that's 14, and 14 plus 4 is 18. 18 into 2, that is going to give you 18 into 2, that is going to give you 36, right? I think I have done it correctly. Plus 3 is 14, 14 plus 4 is, yeah, so 18 into 2 is 36, so that's what I am going to get. Yeah, so 36 is the total valence electron. Now what you need to do, let us call it as A. Okay, let us call it as A. Now you need to calculate B. So B is what, that is 18 into n minus A. Okay, so 18 into n minus A. A means whatever you have calculated over here. N is the number of metal over here. So when you write it down, so it will be like 18. So 18 into n means how many metal are here? So there are 2 tungsten over here, right? So 2 tungsten over here. Yes, Robin, I'll discuss reactions also. Okay, so 18 into 2 minus A means 36. So how much you are going to get? 18 into 2 is 36, and 36 minus 36 is going to give you 0. And your B upon 2 gives you number of metal bond. So since you got 0, so 0 upon 0, 0 upon 2 is obviously going to give you 0. Okay, so number of metal bond is 0. So option 4th is going to be correct one, I think. Okay, so this is how this should be done. So 0 metal bond, if you use this particular formula, we have done it in this way, like 6 electron from tungsten, 5 electron from this eta 5 Cp, that is cyclopentadienyl. This mu Cl or mu chloride, that is going to give you 3 electrons. CO is going to give you 2 electrons each, so 2 CO, so that's why 2 into 2. And now just multiply whole with 2 because we have this twice outside. That is going to give me 36, and then I have solved it in this. So number of metal bond is 0. Answer is option number. Okay, Robin? Fine. Alright, so let's take the next one then. Over here it says that the oxidizing power of these like different oxides. So we have oxides over here given, and it is asked what is the oxidizing power of these oxides. Okay, so how we will do this? So we have like we are given with chromium O4 2 minus, we are given with manganese O4 2 minus, we are given with FeO4 2 minus, right? So what is the oxidation state over here? If you look, so chromium is in plus 6 oxidation state, manganese is also in plus 6 oxidation state, and iron is also in plus 6 oxidation state. So the oxidation state of all of them is same. Okay, now if the oxidation state is same, that means what, that you cannot do this question based upon oxidation state. So because the oxidation state of all of them is given common over here, now you have to go with the size of them. Okay, so if you look upon to the size, order of the size, so when you go from left to right, so chromium is your D, it's a D0 species over here, right? Then manganese is D1 over here, like plus 6. I'm just talking about plus 6 oxidation state, and iron in plus 6 is your D2 species. So they are in this order. So if you write down the order of size, so size order is given by this, that is chromium is the smallest, manganese is in middle, and iron is highest in size. Okay, so if it is so, so what should be the order of this? Yeah, good afternoon, Abhinya. So what should be the answer of this based upon the size? How you can define the oxidizing power of these complexes? How you will do that? Okay, I'm just giving you 2 minutes to think. Okay, tell me what will be the probable answer of it. Sorry, I have just written the wrong order of size. Sorry, the order of size should be this. Size order is this. Okay, this is the order of size. Okay, iron is smallest in size. Okay, so oxidizing power is inversely proportional to size. Smaller the size, more oxidizing power it has. So if you go with these options, iron, manganese and chromium, so iron is smallest in size, so it will have uh, highest oxidizing power. Okay, so which option is going to be correct? So answer number first, oxidizing means it has to undergo self reduction. Okay, oxidize, it has to oxidize the other one. Okay, so it should be so it should be option number one. Okay, so this should be done like that. Understood? Yeah. Okay, let's go with this question. Over here it says for the reaction of this particular complex with PME3, the main intermediate is. Okay, so they are asking about the main intermediate. Okay, very good guys. So they are asking about the main intermediate in this complex. The complex given over here is iron, eta 5Cp, then you have CH3, and then you have CO whole twice. Okay, and you are reacting it with PME3. Okay, so what will happen? What will be the product? Sorry, what will be the main intermediate over here? Okay, so if the oxidation state is different, in that case, what you have to see? Okay, fine. So it's a good question that what will happen if the oxidation state is different. So if something is having higher oxidation state, so that means what it has. So you have to look upon then the more like what it can do if it removes electron. Okay, let's say if something is in iron is in, let's say iron is in +2 oxidation state. Okay, then is it a good oxidizing agent, or chromium in +2 oxidation state? Which one is good oxidizing agent? Okay, so now over here you have to see that iron in +2 oxidation state is a like it's a D6 species, right? And chromium in +2 oxidation state is D3. And also you have to look upon the geometry also. Okay, if they are in, let's say, octahedral geometry, then what you have to see over here that okay, d6 octahedral, that means it can attain, if it removes one electron, it can attain, yeah, so it can chromium in +2, it's d3, right? It's yeah, sorry, d4, d4, yeah, it will be d4. So over here both of them, what they can do, if it removes one of the electron, iron in octahedral species, if it removes one of the electron, it will become d5, and that's a stable, yeah. So that's a stable configuration. So which one is better oxidizing agent over here? So the one which can remove its electron and gain a stable configuration. So iron will be there. Okay, so now that oxidation state will be like that will be a, that will depend upon the environment, what kind of environment is given and what kind of configuration you are getting after removing the electron. Yeah. Okay, Robin, understood? Okay, so like that will be done. Okay, coming back to this question over here, we were having this complex and it was treated with PME3, the main intermediate. They are asking about the main intermediate. So what you will get? See, generally, how we do this question. Okay, both will gain stability. See, okay, fine. Let me just discuss this. D5 will be this, okay, and chromium when it removes one of the electron, it will become D3. Okay, it's though both of them are stable, yeah. This is what, this is completely half filled stable, and this one is like T2G is half filled stable. If you have this kind of like if you have this kind of, yeah, so if you have this kind of situation where you have to decide that which one you have to give more priority, so this has to be given more priority than this one. Okay, because here you're just one of the orbital is getting half filled, whereas over here your electrons are symmetrically filled in all the orbitals. Okay, so your electrons are symmetrically filled means your ligands are symmetrically repelled in all the directions, whereas over here if you'll see, so the ligands which are in the z axis, they will be repelled less compared to the ligands which are in between of the axis. Okay, so this will be given less priority than this when you have this kind of situation. Similarly, if I give you a condition like this, and if I ask a full filled orbital and a half filled orbital, and if I ask which one is more stable, whether a full filled orbital or a half filled orbital, which one is more stable, so we will say the full filled orbital is more stable. Okay, Robin, so this is done in this way. So when you have stable configuration over there also, you can decide that which one will be more stable or more prior than the other one. Got it? Yeah. Okay, clear? Fine. So now we'll go to the next one then. Okay, so iron, this was the complex and you are treating it with PME3. So they are asking which is the intermediate. So generally what we do is we try to see that like your reactant and the product should be 18 electron species, and sorry, your product should be 18 electron species, whereas intermediate should not be 18 electron species. So that is one of the way of finding out that what will be the intermediate. So if you look upon to the options, first thing is that you should just go with the options and just look in the options whether they are 18 electron species or not. Okay, so if you go with the first one, how many electrons are there? So iron will give you 8 electrons, so you'll get 8 electrons from iron, 5 electrons from this eta 5, then 1 electron from this methyl ligand, then you have CO2, right? So that means how much electrons you will get from here? You will be getting um, 4 electrons from here, right? So 4 electrons from here. And what about PME3? How many electrons you will get from PME3? How many electron does a PME3 ligand donates? How many electron PME3 donates? Who will tell me? 4 electrons. How many electrons does a PME3 ligand donates? That's what I'm asking. 2 electrons. Good. So it will be like 19 electron species. It's a 19 electron species. Okay. Next, if you go with option number 2, there you will be having how much electrons? So 8 from iron, 5 from Cp. Then COCH3 will give you 1 electron and CO will give you 2 electrons. So you are going to get a 16 electron species. Okay. Over here, 8 plus 5 is 13 and 3 is 6. Okay, so 16 electron species. Going to the next one, iron will give you 8, then eta 3, that means 3 from here, CH3 will give you 1 and 4 from here. So here you are going to get a 17 electron species, right? 11 plus 12, sorry, it's also a 16 electron species. And 20 electron, okay, let me just count it again. So 8 plus 5 is 13 and plus 6 is 19, right? How it will be 20? 8 plus 5 plus, acha, one I didn't count it, sorry. One I didn't count it because of this CH3, that one I just missed out. Okay, yeah, so it will be 20 electrons. Good. And the last one, if you go, so in the last one you have like iron, it will give you 8 electron, eta 3 will give you 3, then COCH3 will give you 1 electron, CO will give you 2, and PME3 will give you 2 electrons. So overall it will be like 8 plus 3 is 11, plus 1 12, 12 plus 4 is 16 electron species. Now which one will be intermediate? Okay, that's what you have to do. Yeah. Okay, Robin, thank you for that. So now that means all of nobody is a stable species over here. Now you cannot cancel out any of them. Okay, but you should always check the options before going into that. Now let's go with the reaction. So what will happen over here? You have eta 5 Cp. This is attached with iron. You have CH3 attached, and you have 2 CO in this. Now if you have studied reaction mechanism of organometallic compound, you might have seen that whenever in the same complex you have CH3 as well as CO both, in that case what happens? What is the mechanism followed over here? So that is called as 1-1 migratory insertion. है ना? We follow 1-1 migratory insertion. Now due to that migratory insertion, what will be the next thing formed? So that will be like iron over here. Then you will be having CO, CH3, and you will be having CO. Okay, and you are treating it with PME3. So what this PME3 will do, that will come and that will bind to this particular site, making this particular thing like this. So in the next step, yeah, so in the next step what you will get is eta 5 Cp. Okay, so eta 5 Cp Fe, and then this will be like CO, CH3, and then you will be having PME3, and then you will be having CO. So this will be the product. Okay, this will be your product. So what is the intermediate over here? So the intermediate is this one. Okay, this is the intermediate. So eta 5 is there. What is the intermediate? That means you have iron, you have eta 5CP, then you have COCH3, and then you have CO. So which option is correct option? Yeah, very good. Option 2 is correct option. Okay, so you should know about these reaction mechanisms like migratory insertion, oxidative addition, reductive elimination, okay, transmetallation. So you should know about all these reaction mechanisms, that what happens in them. Okay, so I'll be taking two classes over here on YouTube, and I'll be discussing questions over here. So we'll try to cover up as much questions as possible from this topic. Okay, so it's a question from your main group elements. Basically, it's a off-topic question, but yet I hope that all of you can answer it. Just for you guys, I have given this just to see that how many of you can do it. It says the structure of XCF2 and XCO2F2. Let me know in the comment section what will be the answer for this. I'm giving you 2 minutes for that. Okay, you have XCF2 and XCO2F2. What will be the structure of them? Tell me what will be the correct option for this question. HCF2. Just use your VSEPR theory. Okay, use VSEPR theory. Okay, so Robin is saying 3. Okay, Abhinaya also, Neelam also. Okay, good. So if you use VSEPR theory, you will see that xenon has, like, you have to form two bonds with xenon. So you got it, and you have three lone pairs with xenon left. Okay, so the structure will be like, the geometry will be trigonal bipyramidal, but the shape will be in this form. Okay, so it will be like this. Okay, very good, Deepak. So the shape will be in this form. So it's a linear species. Okay, so this one is linear, and the second one is seesaw. How we will do that? If you just draw a rough structure, so xenon, you draw two fluorides with that, two oxygen with that, and one lone pair will be left. So if you just draw it, so again, geometry is trigonal bipyramidal, and the shape is seesaw. How it will be done? So xenon, you will be having oxygen over here, and you will be having a lone pair electron, then you have fluoride and fluoride over here. Which one will stay on the equatorial plane, oxygen or fluorine? That will be decided through the bent rule, that oxygen will be there on the axial position or fluorine. Okay, so which will remain on the axial position, fluorine or oxygen? Which has to remain on the axial position, fluorine or oxygen? Which has to remain on the axial position? Bent rule, you all guys know about it, right? Yeah, so if you don't know about it, I have a video on my YouTube channel. Okay, so do watch that video. Over there I have explained it, that what is bent rule and how it is used. So more electronegative groups goes to the axial position. So on the axial position, fluoride being more electronegative, it will remain on the axial position. Okay, so fluorine will remain on the axial position. Okay, fine, we'll do this question then. It says using the Wade rule. Yeah, good. So it says in this particular question that using Wade's rule, predict the structure type of C2B5H7. So C2B5H7. I hope by now you all know how to solve this kind of question. It's very important and very easy and very scoring also to find out structure of carboranes. Okay, these are called as carboranes. What kind of carborane is it? You all can do, right? So try it. Tell me what will be the answer of it. Okay, Robin, I'll discuss that. Synergistic effect. 2. Okay. Okay, let's do that. Okay, so we have C2B5H7. What we do generally, we take CH units. Okay, one CH unit is equals to one BH2 unit. Okay, so it's recommended that you should take CH common. So there are two carbons, so you have to take out two hydrogen also. So two CH unit. What will be left out? That will be B5 and H5, because two hydrogens you have taken from it in this bracket. Now in place of CH you can write down BH2. So it will become like 2 times of BH2. Okay, and then you have B5H5. Now if you multiply inside, it will be like B2H4 and then B5H5. Overall, you can write down B7H9. Okay, so you can write it like that. Yeah. So it's of this form. Bn, if you have this form BnHn plus 2, so that is closo. If you have BnHn plus 4, that is nido. If you have BnHn plus 6, that is arachno. Okay, so closo, nido, arachno, and hypho you all can do, right? Yeah. Yeah. So it will be like this. Okay, let's go for synergistic effect. Let me just explain synergistic effect. For that, I need a blank slide, and I don't think I have a blank slide over here. Okay, so fine, I'll just explain it somewhere. Okay, let me just explain that. Okay, I'm just searching for a slide. Okay, let's do in this one. So synergistic effect. Okay, because Robin has asked, so I'm just explaining it. So synergistic effect. What happens in this? In this synergistic effect. See, it's very simple effect. It's actually in metal carborane. If you just look upon metal carborane, so you have metal and CO double bond. Now you need to remember, you need to understand two things. That in the carbonyl, like the molecular orbital diagram of carbon monoxide or carbonyl ligand, you will see that the bonding orbitals are filled. Okay, you have anti-bonding empty orbitals. So what you need to know is that in MOT of CO ligand, anti-bonding molecular orbitals are empty. Okay, they are empty. So what will happen if your metal has more electron density? So let's say the first condition I'm just taking, that metal has electron density, or you can say that metal is at low oxidation state. So if the oxidation state of metal is low, so it has more electron density. So what will happen, that those electron density from the metal will be given to this side. To this side means towards the carbonyl ligand. And when it gives this electron density towards this carbonyl ligand, where those electrons will go? They will go in the empty orbital. That means they will go in the anti-bonding molecular orbital. And once this electron density goes to this carbonyl anti-bonding orbitals, what will happen, that first thing what will happen is that your bond order of CO decreases. Okay, it will decrease bond order of CO. Secondly, if the bond order decreases, bond strength of CO also decreases. Fine. And your frequency, carbonyl frequency, will also decrease, and bond length of CO will increase. So these things will happen if your electron density on the metal is more. Okay, or electron has more electron density. Second case is like if metal is in high oxidation state. Okay, no problem. High oxidation state. Let's say if the metal is in high oxidation state, so what will happen, that metal is now electron deficient. Okay, so now what will happen, since metal is electron deficient, so what will happen, that in the d orbital, so see how this bonding is being done. There are two types of bonding. These are metal d orbitals, and this is carbonyl like pi orbitals. Okay, so this is how we have orbitals over it. And there is one more orbital that is called as, that is the sigma bond between the metal and carbon. So now if metal is in high oxidation state, metal, so earlier what is happening, these electron density from metal to carbonyl is shifted in these orbitals. Okay, in that, from the d orbitals, from d orbitals of metal to the carbonyl ligand. And once if the metal has high oxidation state, in that case the reverse will happen, your electron density will come from carbonyl towards the metal. And what this will do, what this particular thing will do, it will do all the reverse of it. Means the bond order of CO will increase, bond strength of CO will decrease, carbonyl frequency will decrease, and bond length will carbonyl frequency will increase, and bond length will decrease. So all this will happen if metal is in high oxidation state. Now this effect is called synergistic effect, because it's a effect which is like happening for both of them. When the carbonyl needs the electron, metal gives it to carbonyl, and when the metal needs electron, carbonyl gives it to metal back. So this is the only effect called as synergistic effect. It means the effect is happening simultaneously. Electron shift of electron is being done from metal to carbonyl and from carbonyl to metal. So that's the only thing over here. Okay. So synergistic effect is also seen in your metal alkynes, sorry, metal olefin bonds also. So there also the same thing happens, and there also you'll see the same effect on the bond length and the bond order. Okay, so like that, it was your synergistic effect. Okay, let's take the next question. All right, so let's talk about this one over here. It says, this question over here says that the intermediate and the final major product of photolysis of Z. So this is the compound and you are doing photolysis of it. So what is the intermediate and what is the final product in this case? So that's what they are asking. So first of all, just look upon this complex and just see that whether it's a 18 electron species or not. So we have molybdenum, we have 3 CO attached to this, and we have one ligand. This one is the ligand. Okay, so let's count down whether it is 18 electron species or not. So molybdenum will give you how many electron? It's again a d6, like it's a chromium, sorry, it's not d6, it's a chromium group element. So 6 electrons you will get from your molybdenum, 5 you will get from this eta 5 Cp. Then each carbonyl will give you 2 electrons, so 2 into 3 you will get over here, and plus 1 because of this ligand. Okay, this allylic ligand. So you will be getting how much? 6 plus 5 is 11, plus 12 and plus 6, it's giving you 18. So it's a 18 electron stable species. Now it has to undergo reaction and it has to form an intermediate. So how it will form intermediate? Now see over here, few things you need to know. First thing is that whether in the same molecule, what will happen in the next step. Okay, so if you do the photolysis of this, so in the next step what will be formed? So an intermediate, and that intermediate will not be 18 electron species. Intermediate will be lower in from that 18 electron species. So do the options, like like check the options whether they are 18 electron or not. Option number 1, if you go for option number 1, that will be like you will be getting 6 from molybdenum, then you will be getting 3 from this ligand, from this particular ligand, then you will get 3 from this ligand because the hapticity is 3 over here, and you will get 6 from this carbonyl. So it's a 18 electron species, so it cannot be your intermediate. Okay, so A cannot be your intermediate, that's what you can see. If you go to option number B, over here also you will be having like 6 from molybdenum, 5 from this eta 5, and then you will be having from each CO, you will be having 2 electrons, so 4 from there and plus 1. So you will be having 16, right? So it's a 16 electron species. Yeah. So it's a 16 electron species. It can be your intermediate. Okay. So this is one of the probable answer which could be intermediate. Going to option number C. If you go with option number C, so option number C is like 6 from molybdenum, 5 you will get from Cp, then you will get from each CO, you will get how much? From each CO you will get 4 from here, and then uh, yeah, so you will get 3 from here because 1 from this sigma bond and 1 from this acoustic, sorry, 2 from this acoustic interaction. Okay, yeah. So option C also has how much electrons? So 6 plus 5 is 11. 11 plus 4 is your 15 plus 3 18. So C also cannot be your intermediate. So C is also not your intermediate. Going to the option number 4. Option number 4 also has like 6 electron plus 5 from Cp plus 4 from carbonyl and 3 from there. So if you go with this, so again it's a 18 electron, right? So again it's a 18 electron species. So only intermediate which is possible over here is your option number B. So B can be your intermediate. Okay, so B will be your intermediate. Now what will be the product? So product has to be 18 electron species. So which one will be the product? Whether, so B is your intermediate. So either option 2 is correct or option 3 is correct. Okay, so yeah, so what will be the product now? So our product will be D. Why product will be D? Why not C? So just look upon structure of both of them. So if I just draw a structure of C, so it has two CO ligands, it has this, and then you have this. Okay, so this might have formed, this is formed when your CO got inserted. Okay, one of the CO got inserted and then it is formed. Okay, so option number C is formed after 1 migratory insertion. Migratory insertion. But if you look upon option number B, you can easily see that there is no insertion happening because it's the intermediate, right? So you have to derive product from the intermediate itself. So in the intermediate, you are just having 2 carbonyl, whereas if C might be the product, so in C you are getting 3 carbonyls, which cannot be possible. Okay, so okay, I'll tell how many NMR signals in D. Okay, we'll go for that also. So C will be wrong answer because C is not the correct answer. Okay, now D is the probable answer because here you have 18 electron species are also there. Hapticity of this ligand has been changed, so it has been derived from the intermediate itself. So D is your correct option. So overall correct option is option number 2. Now the question which Deepak has asked is how many signals we will get in D. Okay, I'll just draw it. Option D first of all. So we have molybdenum, we have CO, we have CO, and we have this. Okay, now if you look, first thing is that okay, so how many signals you will get over here? So for any of these kind of questions, the question which is asked is how many signals you have, that is asked at normal room temperature. Okay, if you go at lower temperature, what will happen that these for all these 5 protons will have different NMRs, they will show different NMR signals. Okay, because of the fluxional behavior. So since at normal room temperature, if I just ask at normal room temperature, so you will say that all these 5 protons are equivalent and they will show one signal because of them, and these protons which are over here like this CH2, CH2, and this is also CH2, right? So these 2 they are also equivalent, so the signal which you will get is 2. So overall you will get 2 signals in proton NMR at normal temperature. Okay, so 2 signals. If I just ask you that what will happen at lower temperature, if at very low temperature, so you will say that these among these 5 protons, um, okay, so since the hapticity is 5, they all see among these 5 protons they are with different chemical environments, right? This is along with CO, this is some of them are along CO, some of them are towards this. So at lower temperature they will have different chemical environment because now the hapticity will be stopped over, like the ring current will not happen over there, and these protons will show different chemical, like will show different peaks. So they will be like 1 2 3 4 5 peaks over here, and similarly here you will have 3 peaks. So overall 5 plus 3 means 8 signals you will get over here. Okay, so this happens like this depends upon the temperature at which you are measuring that. All right, so we'll take one more question. It says that the reaction of Mn2CO10 with I2, that means with iodine, results in A without loss of CO. So CO is not lost. Compound A on heating at 120 degrees Celsius loses a carbonyl ligand to give compound B, which does not have manganese-manganese bond. Compound B reacts with pyridine to give two equivalent of compound C. Compound A, B, and C are. Okay, so you have to tell what are compound A, compound B, and compound C. So if you just look at the reaction, just draw the similar, like just draw it in the usual way, then also you will be able to predict the answer over here. See, you are treating it with iodine and you are forming compound A. Okay, and there is like and there is no loss of CO ligand, so that you have to keep in mind that there is no loss of CO ligand. So CO should be 10 over here. Now compound A, if you heat that at 120 degrees Celsius, you form compound B with loses a CO ligand. Okay, so loss of CO ligand is done over here. Now if you go further, which does not have, okay, B which does not have MN bond, that is also given. Okay, B does not have MN bond, so there is no MN bond in B. Now compound B reacts with pyridine, you are reacting it with pyridine to give compound 2 equivalent of compound C. So 2 equivalent of compound C. Okay, so you have to see over here that what is happening in this reaction. First one, over here you are treating it with iodine and it's given that there is no loss of CO. So that means there should be 10 CO in the complex present. So just look upon the options, in which option you have, okay, sorry, you should have a compound along with iodine, and there can be manganese, there should be manganese bond. Okay, so that's what in the first statement it is said. So you are treating it with iodine, and you are having 1 2 3 4 5 6 7 8 CO over here, 2 iodine over here, manganese bond is also present. Okay, so this is your, okay, so compound A they have asked, right? Which one is compound A? Okay, so let's do it one by one. Okay, yeah. So compound A is formed where you should, this one. If you just draw Mn2CO10, how this will look? Mn2CO10. So Mn2CO10 will look something like this. Okay, so if I just draw Mn2CO10, so the structure of this compound is, just find out metal bonds in this. Okay, so how many metal bonds you will get in Mn2CO10 in this complex? How many metal bonds you will get? How many metal bonds you will get? One metal bond. Okay, Deepak, good. How many metal bonds? So you have, let's say, from manganese you will be having D7, so 7 electrons, 7 into 2 because 14 from here, and then 10 into 2. So 14 plus 10, yeah, so one metal bond. Okay, so 7, this will be like 14 plus 20, so you'll be having 34, and if you solve it further you will get one metal bond. So manganese bond is 1, and rest you have to make carbonyl attached to that. Okay, so 5 carbonyl to one of the manganese, 1 2 3 4 and 5, and similarly 5 carbonyl to the other. Okay, now if you look, is it a stable species? So 7 8, and yeah, it's 18 electron species. Okay, yeah, good. So this is the structure of it. Now if you react it with iodine, what will happen now? If you treat it with iodine, obviously manganese is already both these manganese are 18 electron species. If you treat it with iodine, it will not react unless and until this bond will break. So this bond will break and you will get a species having 5 carbonyls attached to the manganese. Okay, 1 2 3 4 5, and iodine attached to that. So that means you will be getting this as your A. So this is your A. Okay, so we got A. Now this A, if you heat it at 120 degrees Celsius, there is no loss of your yeah. So there is no loss of your CO ligand. That means you should have the same number of CO ligand. Okay, sorry. So it's given that there is no loss of CO ligand and A is formed. Now if you heat it with at 120 degrees Celsius with the loss of CO ligand, you are forming B, which does not have manganese bond. So there should be no manganese bond. So what will be B? So if you look in the options, there are only two options where you have manganese bond. But B, there is like up till B, there is no trace of pyridine. So pyridine will not come in this case. Okay. So option number third is wrong. Option number like 5 is correct for B. So A we got as the second structure. B we got as the fifth structure. Okay. Now talking about your C product. So it's given that if you treat that thing, that means if you treat this particular complex with pyridine, so what you are going to form? So two equivalent of C. So that means again the fission has happened if this bond has been broken, and then you have formed C. So if you break this particular bond like this, so manganese will have one of the place available for the bond formation, and that will be through pyridine. Okay. So two equivalent of this only can be formed. So your C is your fourth species, fourth given structure. So answer will be option number 1. Okay, so one by one you have to check, and then you can go with the correct answer. All right, clear to everyone? Okay, so now I'm going to take the last question for this class. Okay, last question, and rest of the things we'll discuss in the next class. Alright, so over here in this question it says among the following species isolobal to CH2 are the species which are isolobal to CH2. So isolobality, it is asked from isolobality. Okay, so CH2, how much electrons it has? CH2, in the CH2 unit you will be having 6 electrons. So generally isolobality is done in this way, that if something has 5 electrons, it is isolable with 15 electron species. So if it is a main group element, okay, and this is transition element, transition complex basically. 6 electron species is isolable with 16 electron species. 7 electron species is isolable with 17 electron species. 8 electron species is isolable with 18 electron species. Now in this given question we have CH2, that is 6 electron species. So you have to check in the transition metal complex that where you have 16 electrons. So if you go with the option number A, so I'll just write down over here. So option A will have like Cp means you will be having 5 electrons from that cyclopentadienyl. Chromium will give you 6 electrons. Each CO will give you 2 electrons. So that will be 4. So you'll having 15 electron species. Okay. So option A is not the correct answer. Checking option B. So Cp will give you 5, and copper, how much electrons you'll get from copper? So 11 electrons from copper, right? I am doing everything from the neutral electron count method. There are two methods to count. One is neutral electron count method. The other one is oxidation state method. You can follow any one of them. I feel easy to use neutral electron method, so that's why I use that. Okay, so it's a 16 electron species. So option B is your isolable species. Like it can be isolable. Okay, C, if you go with the option number C, so here you will be having like nickel will give you like it will give you 10 electrons, right? Yeah, so nickel will give you 10 electrons and plus 4, so it's a 14 electron species. So that is not going to be your correct answer. Okay, so that's not correct. Talking about your D, so your D option will be like you will be having 5, sorry, chromium will give you 6 electrons and plus CO4, that means 8 electron from it. So again 14 electron species this is. And the last one is your 1 minute. And the last one is your E option. What is over here? It's FeCO4. So if you go with this, yeah, if you go with that, iron is 8 electrons and then you will be having 8 from here. So it's a 16 electron species. Now if you look, only option B and option E are having 18 electron species. You know, option B and E are your complexes which have 18 electrons in them. But in options there is nothing like B and E. Okay. So I think this was asked in CSIR June 2019, yeah, June 2018 I think it was asked. Okay, and this was a wrong question which was taken in the exam, and later on they have given correct answer in the answer key as option number 3. So this was a wrong question in CSI net exam where like all the species were not in the options, you were not getting isolability, but yet since B and E were in the option number 3rd, so they have given it as correct one. But in the answer key they have just marked star, so that means anyone who has attempted this question, he or she might get the answer. But since we are practicing it, so the correct answer is B and E, not C. Okay, according to this, C is not the correct one because it's a 14 electron species. Okay, understood? Clear, everyone? All right, so that's all for this class. I'll end up over here. And now regarding my next class, so I'll be taking two classes on Sunday, that is tomorrow. Okay, so Sunday we will be having two classes. One will be at 10 a.m. and the other one will be at 12 noon. Okay, so at 12 noon I'll be taking quantum chemistry, and at 10 a.m. I'll be taking inorganic chemistry as the topic. Okay, so tomorrow morning we'll meet at 10 a.m. and at 12 noon. All right, so see you guys tomorrow. Till then, have a great day. Bye bye. Take care.